as a reference page. Okay, that's me. What I will talk? I will talk about the comparison test. That's me. Let's start. Okay, now looks better. And what we have? Let's consider infinite series like this one. Series from 1 to infinity, 1 over 2 to the n plus 1. That means you probably remember the geometric one, because that's also another tool, another property. If n is placed only in the exponent, we will all recognize that this is the geometric series. However, we can't really have like additional subtraction like terms. That means this is not really the geometric one, because if I will try to compute a common ratio, it will be not common actually. That means this will be not a difference, the multiple difference of each terms. That means this looks like the geometric, but it's not really the geometric one. Okay? That means this is the point of this test. We may try to consider this one just 1 over 2 to the n, okay? Because this one is definitely the geometric series, right? We can see 1/2 is the common ratio, which means it's convergent. We don't have to compute the sum at the moment, because we're just looking for the simple answer, if the series converges or diverges. If converges, we don't have to find the sum at the moment. Okay? That we all know definitely this. That's what I would like you to know right away. The common ratio is 1/2, because only 1 and 2 is like 2 in the denominator is taken to the power of n. Okay, but now, like how can I compare? Because the first thing, in order to use the comparison test, we always have to look at our original problem, which is this one, and we have to create something simple to compare with our original series. And that's what I did. I did create a new series, but we can see it's almost the same. That means something simple that we will know almost right away if it's convergent or divergent, and something comparable. And now, how can we compare? Because I can, if I will rewrite the terms, 2 to the power of 1, addition, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, maybe one more, 2 to the power of 5, and so on. Okay? That means that's all of my terms. Now, let's try to rewrite these terms. This one has just denominator 1 more. That means 2 plus 3, 4 plus 1, 2 plus 1 will be 3. 4 plus 1, 5. And then 8 plus 1, 9, 17, 33, and so on. That's what I will be looking for. If I check the corresponding terms, okay, I see that each of the terms, like 1/2 is definitely greater, or I can say this way, 1/3 is smaller than 1/2. 1/5 is smaller than 1/4. 1/9 is smaller, and so on. That means each term I can write like that. Okay, each term of my original series, it's smaller the corresponding term, of course, for the corresponding n's. That's what I'm trying to show you. My inequality sign looks funny. That means I'm trying to compare these. 1/3 is smaller, 1/5 is smaller, 1/9 is smaller, and so on. But we will not really use the expanded form all the time. We will just use the shortcut, the inequalities. That means each term, 1 over 2 to the n, it's greater than this one, than the original one. Or I can say maybe the other way. The original terms, the corresponding terms, are smaller than this. And this is also a shortcut. We know that this infinite sum exists, it's 1. That means exists as a finite number. It's finite number. Everything what is smaller than the finite number also must be the finite number, which in our terminology, convergent. That means if this one is convergent, and we even have this luxury to say that it's convergent to 1, Okay, but as I said, we have to just know that it's convergent. Everything what is smaller, that means this relationship, this inequality, it's extremely helpful, okay, and appropriate in this case. Everything what is smaller is also convergent. Okay? That means that's how we use comparison, and we call comparison test. Let's see. Yeah, I have few more comments, and then I can show you the test. That means, of course, it is convergent. Our original series is less than 1, then must be convergent. The only thing is, when we're trying to compare all of the terms of the series, they have to be positive. Let me come back for now. You can see we have all of the positive terms, because as soon as we have maybe the alternating terms or some terms positive, some terms negative, then we know how inequality, then we can't really distinguish a proper relationship. Because I can have 1, 2, 3, I can have, I don't know, 10, 20, 30. Of course, this is greater, but as soon as I put negative, oh no, maybe this way, as soon as I will put negative, this become greater. Okay, that means we can't deal, because we will have really messy solution. That means all of the terms, they have to be positive terms of the series in order to compare. Oh. Okay, please remember, that's important. If some of the terms are negative, no, we can't use the comparison. Okay, and that's the test. Let's see. Suppose that the series A sub n and series B sub n are the series with the positive terms. That's what I'm trying to stress out. And then that's how we can compare. If the B sub n is the new one, okay, that's my new one. That's the job for us to find the B sub n, the series that we're gonna compare with this one. And this one is the original one, that's given. Okay, if B sub n is convergent, and we have this relation, we remember everything is smaller. My original series is smaller than B sub n. For all of the n's, then my original series is convergent. That's what I was showing you. Or we can also use the comparison for divergence. Let's assume that B sub n is divergent. Okay? B sub n is divergent, and we suddenly have this relationship. My original summation, or the corresponding terms, are actually greater. Greater than my B sub n. That we also, we think that divergent is kind of like huge. We accumulating huge number, infinity. Oh, the series could, I mean, we can have undefined situation, but let's imagine that divergent means like unbounded. It's like, it's huge number. Everything what is greater than infinity, in this case, I can say, it's also divergent. That means if B sub n is divergent, and we have this relation, then I can conclude, I can say that A sub n, my original series, is divergent also. Okay? We can't conclude the other way. Yeah? Let's say this. That's what I'm trying to explain. If B sub n, let's say, is the series B sub n is convergent, exists as a finite number, S exists as a finite number, then having this relation, yes, having my original series, terms of the series greater than this, yeah, I don't know, I can't conclude A sub n might converge or may actually diverge. Because something that is greater than my finite number, I don't know, could be the finite number or could be divergent, could be infinity. That we may have a situation that the comparison test doesn't work, right? And this actually comparison test, we will call direct comparison. Direct comparison test, okay, which we will call DCT, because we directly comparing, right? That we really have to make sure what relation we have, right, between A sub n and B sub n series, and then if new one, the B sub n is convergent or divergent. Okay, that means I have lots of examples. Hopefully we can understand the idea. And yes, you can read this. That's what I explained. Sometimes we can't apply. It will be inconclusive. Okay, that means let me show you the entire slide. As I said, the B sub n we have to create. Okay, that means most likely we will use we will compare with the P series. Yeah, we just learned about this one because it's nice and simple. If we can compare our given formula, complicated formula, with something simple, will be so easy to make determine convergence or divergence. Also with the geometric one, because we know based on the common ratio, we know right away convergence or divergence. Or simply like the rational functions. If we have rational functions, numerator and denominator, we will always look at the highest power. Always we can take the highest power from the numerator, highest power from the denominator, try to simplify, and probably we will simplify to the P series, and then we will try to compare our given series. Okay, that's like just the hints, but you will probably get the idea. Let's see. I have lots of problems, and probably I'm always saying this message: never miss any question that is solved in the session, in the live weekly session. Okay, and of course, additionally, the practice with Kasia. Okay, let's start. Exercise number 1. Question will be the same for the next hour. Okay, and we have to just determine convergence or divergence. And what we have an infinite series from 1 to infinity, 5 over 2n squared plus 4n plus 3. That's what we can see. It's maybe too much. Maybe I can try to integrate, like you learned the integral test yesterday, but that's too much. Comparison is nice and quick, of course, if we can use it. That means I will say that this function, okay, all of these terms, and that's what was said. We can take just the leading functions. On the top, I have no option. I have only 5, but in the denominator, that's my leading function. Okay, that means I'm trying to compare these two functions at the moment, terms, because that's the terms, corresponding terms, if n is 1, if n is 2. But what I see, numerators are the same. Denominators, on this side, I do have a little bit more because I'm adding 4n and I'm adding 3. That means if the denominator is greater, the whole fraction is smaller. Okay, because we remember, that's important. We have to know this relation. Okay, and I will not rewrite, I will just add, actually I can use the red color. That means this infinite series is greater than this one, the terms, the corresponding terms. Okay? And what I see here, I can put 5 over 2 as a constant in front, but the main thing is 1 over n squared. Okay? I can actually simplify here. 1 over n squared, from 1 to infinity. And what do you think? You have to tell me. Is this infinite series convergent or divergent? 1 over n squared. Okay? Yeah, get ready for typing. Faster, because, yeah, convergent, because, and why is convergent? This is my B sub n, converges by, of course, because the P is 2 and it's greater than 1. This is like B sub n. I will always call the new one B sub n. Okay, and now we can see if this is convergent, this exists as a finite number, we're not going to find the number. But this exists, this sum exists as a finite number. Everything what is smaller, it's also finite number, convergent. That means my conclusion, it says that this infinite series, okay, converges, but please remember, not by the P test, not by this blue notation, by direct comparison test with, and what we comparing with this one. Because we will always ask you what you're comparing with. Okay, that's the final answer. Nice and easy. Yeah, we can see we have the statement. Converges by direct comparison. Direct comparison test. Okay, exercise number 2. Determine whether the given series is convergent or divergent. What do you think? It's going to be convergent? Probably you can tell me right away. Of course, because I do have quite similar situation. I have this function and I'm taking leading function, which is just 1, and leading function. And adding 3 in the denominator, this makes the whole fraction smaller, because if the denominator is bigger, the whole fraction is smaller, which means that's the relation. And let's add the summation, because of course we're thinking about all of the terms. And I can cancel out that too now. And the same situation, yeah, almost the same. This converges, B sub n. Converges, and I can say because P is greater than 1. And then everything what is smaller also is a finite number. My original series A sub n converges. Converges by direct comparison test, and I did compare with 1 over n to the power of 5. Okay, excellent. I really would like to box the final answer. Maybe I can use the green color. Okay, just to make sure that we know what is the final statement. Okay, another one. Determine whether the given series converges or diverges. Inverse tangent of n over n squared. And I did type starting from 3, doesn't matter. We can always skip a few first finite numbers, starting with 1 or 2 or 3, doesn't matter. We're looking what is happening at infinity. And what do you think? It's convergent or divergent? Okay, too difficult, let's say. Let's see. That's what I will do with this one. I have no option because I can't really take something else, like to build my new series, n squared, n squared. But what do you think? What is the nice number to compare with inverse tangent of n? What we know? Do we know something how inverse tangent of n behaves at infinity? Pi, exactly. Ta inverse tangent is never greater than pi over 2. Let's see how fantastic B sub, like the new series we did create. I can draw, because we know inverse tangent looks like that, but we're not taking everything since we just talking about a series. That means this is pi over 2. We do have a horizontal asymptote. And negative pi over 2. We're not even looking at negative. But the terms of the sequence are like for inverse tangent of 1, inverse tangent of 2, inverse tangent of 3, 4, 5, and so on. That's we're only looking at these dots. But the dots, the values of this, of inverse tangent of n, they will follow the yellow path, right? The yellow, that's the shape. The same thing will be never higher than pi over 2. Okay? That means this is excellent series to compare. Okay? Oh, I can keep 3. Doesn't matter. Okay, and then I can put the constant pi over 2 in front and 1 over n squared. And we all know that 1 over n squared is convergent because p equals 2 is greater than 1. That means this converges, everything what is smaller converges too. And that means let's write the final statement. my original series A sub n converges by direct comparison test with, and we did compare with pi over 2, 1 over n squared. Right? It's really important to state what we're comparing with. Okay, that means I can just do one more thing. What we did important, we did compare inverse tangent of n with pi over 2, because that's what I always have the question, like, how do I know what to compare with? But we can see, based on these examples, we can learn. That means this is one common, extremely common comparison. Yeah, we can eliminate like the complexity. Okay, example number 4. Determine whether this infinite series is convergent or divergent. Sine square of n over n squared. And what do you think? It's convergent or divergent? The same thing. I have to keep my denominator. I have no option. I can't change it, because if I will change for something, it will be not easy to compare. And what do you think? What I can put here? Do we know possibly the maximum value of the sine function? And even if I will square it, probably will stay the same. Oh, we don't know maximum value of sine function? You do know. Are you there? Okay, this is sine function. What's the maximum value for sine? What is this now? It's 1. Thank you. Yes, you have to participate. I know that I don't see you, but I mean, I see your names. And it's nice that you attending the session. But okay, that means this is just sine function, okay? But if we will take sine squared, all of the positive will become, all of the negative parts, we will square it and we will have on the top. And still 1 squared to 1 squared, it's still 1. That means the graph of sine squared looks something like this one. But still, the maximum value is 1. Sine square of n is never greater or could be equal to 1. And we can see nice comparison right away. We can also start with 3, doesn't matter. Okay, and then this one is definitely convergent. Okay, because p is equal to 2 greater than 1. Then my original A sub n series converges too. Converges by direct comparison test, and we comparing with just 1 over n squared. Yeah, everything works. And let me. Another thing that I didn't actually with exercise 4, you probably notice all of my terms that we just comparing are positive, because I supposed to always say this, A sub n is positive always, all of the terms. Yes, we can see if I will get back to the previous one, it's also positive. It's also positive. And this one is definitely positive. I think please remember, because we can't, if we have negative, we can't really compare. Okay, and what we did here, it's also worth to remember, I did sine square of n compare with 1. Okay? It's worth to remember these comparisons. Okay, determine whether this series is convergent or divergent. The series from, I don't know why, because I know why I put 3. I will tell you. Let's put 1. From 1 to infinity, negative 1 to the n, plus 7 over n squared, n to the power of 4. Okay. 7 is actually saving me, because negative 1 to the n could be positive 1 or could be negative 1. That means this will be a different number, like, I don't know, plus 1/2, right? Then I will have a problem, because negative 1 plus half is negative half. Then I can't use the comparison. But 7 is a good number. Okay, that's what I will be comparing. Again, I will not change my denominator. I'm picking the leading function, and it's actually the only function. And what do you think? What is the maximum or minimum? Depends what we need. Value of the numerator. Yeah, it's actually 8. Thank you. I was gonna write something because this quantity could be positive or negative 1. That means my numerator only like change between 6 and 8. 6 and 8. 7 plus 1, 7 minus 1. Okay, that means, and I think I need this. Let me, okay, I will, because I would like to show you something else. Okay, that means 8. And this is, of course, probably looking at me doing all of this, you will be an expert with comparison. And I can put that 8 in front because it's constant, n to the power of 4. And thank you for participation. Thank you. And n to the power of 4, 1 over n to the power of 4, of course, is convergent because P4 is greater than 1. Everything what is smaller, I will highlight this, it's also convergent. Convergent by direct comparison test. And we're comparing with this, right? But what I think I did pick the green color. Okay, and we're comparing with this one. I'm saving a little bit of writing. But what about if I will give you example, let's say 5a, because I would like to show you how we can balance with this. Negative 1 to the n plus 7 just over n. Okay, that we can see what I did. I did drastically change the denominator. That means I will have negative 1 to the n plus 7 over n, and I will try to compare. I have to put n. And I can try the same. Can you see this? I can put 8. But then I know my relation, then 8 is the maximum value, this will be smaller. And what we know about this infinite series? 8 in front, 1 over n. It's 1 over n convergent or divergent? Do you remember from the, it's of course divergent. That means, let me put this 1, 1. That means this is definitely, I can put 8 in front one more time. This is divergent, and I can't change this. This one is divergent. And I can say harmonic. Harmonic series, 1 over n. That's when we can see if this is divergent, like let's say infinity. Something that is smaller than infinity, I don't know. I can't use the direct comparison. It could be infinity or could be actually convergent. I don't know, could be the finite number. But what we can do, instead of 8, what is the minimum value? What will be the minimum value of this numerator? Yeah, do you remember? Because sometimes we will be adding 1 and sometimes we subtracting 1, because negative 1 to the odd number is always negative 1. That means 7 minus 1, 6. Then this is always greater. Always. Because could be 8 also. Okay, that means greater or equal to. I mean, we can also have. And now I have no problem. This is divergent. Something that is greater, it's also divergent. That means divergent means like huge, infinity, unbounded. Everything what is greater than unbounded, it's also unbounded, divergent. That means this infinite series diverges by direct comparison test, and please make sure that you put 6, not 8. Yeah, because 8 will not work. 8 will not work. Please remember that. This is actually a good example. to show you. And actually, we're lucky that we have this, that we can manipulate this relation. That means it's important to have 6. We know why. Okay, let's keep working. Exercise number 6. 6, 6. Okay, this infinite series from, now I should put maybe 3. Okay, or 2. I can't put 1 because what's the value of ln of 1? Can you tell me what is ln at 1? Oh, natural log, it's 0, right? That's when we always actually put 3 because we like the, what we like? We like the characteristic of natural log of n, like after the e value. And e, of course, is 2.771, but n is just the counting numbers. That means the first integer after this is 3. That means most likely you will always see that starting from 3 because everything works nicely. Okay, oh yeah, we have to this, we can't have 1. Okay, that's what I have. I have just ln of n. And I can tell you, I can start from the end maybe. If you see the natural log of n, you can try to compare with n sometimes. Actually, I have to say that you can compare with everything we can compare with everything what you feel comfortable with. Of course, we have to have some feelings, some knowledge, and some experience, some practice, some confidence. Okay, that's what I'm giving you some hints. But remember, you can compare with everything. That means looking at the graph, natural log of n, that's my function, or I can say, and looking at, that means this is ln of n, and looking at just n, just like x, we can see that n is always greater than ln of n. Okay? That means maybe this works, okay? If not, we may try to compare ln of n with 1. 1, it's simply a horizontal line, okay? Like just 1. And my new series is just 1. The only thing is, that's what I was saying, function ln of n is greater than 1 starting at the point e. That means for all n greater than 3, because e approximately is 3. That means this is some comparison that you may use, okay, for n. ln with n this way, ln with 1 this way. Let's see. I will put n for now. That means what I'm doing, I know that n, function just n, it's or series, sequence, n, it's greater than ln of n. But having bigger denominator, the whole fraction is smaller. Okay? Starting with 3, we do have relation. Okay? Because just starting from 3. And we know that this one is divergent, harmonic. Okay? Then everything what is bigger, it's also divergent. My original series A sub n diverges by direct comparison test, and we comparing just with 1 over n. Okay? But again, that's some hints for you, that you may try to put n or 1 instead of ln of n. Or you can try different things. You can really try almost everything. Okay, let's box the final answer. Okay, divergent with this. Okay, exercise number 7. Oh yeah, that's what I'm just saying. That's the same, that the notes that we may start not exactly from 1, I will even put, we can start from different number, but that's fine. Okay. Check the convergence or divergence of this infinite series from 3 to infinity, ln of n over n. ln of n over n. Yeah, similar. I know that is perfect for integral test, right? If you remember from yesterday, because we can nicely integrate this oh yeah, I have to put everything in terms of x. But integral test, it's beautiful tool, but too long at the moment. Because I can copy maybe n, and instead of ln of n, I can put 1. Well, I don't want to change. And then ln of n, if we look at this function, can you see ln of n, it's after 3, after e, it's above 1. That means this is greater. And the same situation. This is harmonic series, it's divergent. Harmonic series, divergent. Everything what is greater than unbounded sum, it's also divergent. That means my original series diverges by direct comparison test, and we comparing with 1 over n. Actually, I can rewrite. No problem. Let's start with 3. Okay, that's my final answer. Exercise number 8. Yeah, you can see it's lots of problems. Don't miss any of them, none of them. Okay, now you can tell me. Can you tell me how can I compare? What function I will put? What I will put in the numerator, what I will put in the denominator? Okay, denominator first. What shall I put in the denominator? Of course, to have nice, of course, thank you, Jessie, just n to the power of 4. And now I think it's the luxury problem, because we may try to put 1, or we may try to put n. Depends what we need. Let's put 1. I don't know if it's a good choice, but let's do it. And we remember that function ln of n behaves like that. 1 is just the constant. That means ln of n is greater than 1 at starting from 3. And what do you think? Is this good relationship for this condition? I'm adding the summation. What do you think? 1 over n to the power of 4 is convergent. Can I conclude convergence having this inequality? This is finite number. Something greater than the finite number? I don't know, right? That means that's not a good choice. Okay, let's remove it. And we have this, as I said, I can put n. And function n looks like that. That's n, that's ln of n, and that's 1. And it's always greater than ln of n, because we're comparing numerators, since denominators are the same. I can simplify this one, of course, and I have 1 over n cubed. Excellent. This one is convergent by p being 3 greater than 1. Everything what is smaller than the finite number, it is a finite number. Okay, that means this one. Okay, I can use the green color for writing. My original series A sub n converges, okay, by direct comparison test, and now we're comparing with 1 over n cubed. It's extremely important. Okay, we're comparing with 1 over n cubed, not n to the power of 4. We can see, because otherwise we have different inequality. Right? That means one more time, ln of n, n and 1. That's bigger, that's bigger. You may try to use these comparisons. Okay, exercise number 9. Determine whether this series is convergent or divergent. 2 plus sine of n over 4 to the power of n. What do you think? What we will replace? with 4 to the power of n. I have to keep this. Probably I will keep this. And again, what is the maximum value of sine function? Sine of n. What's the maximum value? Oh, I did ask you this question today. We do have some people in the classroom. It is 1, right? Maximum value. Then sine of n, yeah, it's always less or equal to 1. I can add 1. And I did create really nice series. That means this is my original one, complex one. This is my new one. And I will have 3 over 4 to the power of n. I hope everybody recognizes what type it is. What type of infinite series is this one? Or what tool I can use to prove it? Convergence or divergence. Oh, this is the geometric series because n is only placed in the exponent and we don't have any other like addition or subtraction. Geometric series with, and who can tell me the common ratio? The common ratio R is just the number taken to the power of n. Oh, 1/4. I know that you know, you just don't want to type. 1/4. That means 1/4 is less than 1. This geometric series is convergent. Okay, convergent. Everything what is smaller, that's what I like it. Everything what is smaller, it's actually convergent too. Okay, this is my infinite series A sub n converges by, and please do not write geometric one. We're still using comparison test and we're comparing with this. Okay, everything must match. Okay, you can probably see if I will put -1, I have this possibility to change the relation. Everything depends on the denominator. If, for example, n will be in the denominator, n, then and we know n in the denominator, probably I will end up with harmonic one. That means I will switch the inequality right away. I will put -1 and then I will have 1 over n. But okay, I'm just trying to create different problems, possibly for your test. Okay, and example number 10. Infinite series from 1 to infinity, e to the power of 1 over n over n. You can probably tell me, yeah, can you tell me like right away, do you have some confidence after these 10 problems? It's gonna be convergent or divergent? No feelings, because I will keep my n in the denominator. Okay, and what shall I put here? Let's see, 1 over n behaves like that. 1 to the power of 1, e to the power of 1, e to the power of 1/2, e to the power of 1/3, e to the power of 1/4, and so on. That means, what is this? If you would like to have let me just check the limit, the behavior of this. That we can see that the terms are definitely getting smaller and smaller. Yeah, I can, I use entire slide, but it's okay. For 1, we have e. For 2, we have square root of e, right? For 3, we have cube root of e, because it's cube. That means the terms are getting smaller and smaller and smaller. And what do you think? What will be the limit, the behavior at infinity? What is e to the power of 1 over n? What is this limit? E to the power of 0. Thank you, Katne. Yes, e to the power of 0, because this is, if this is infinity, 1 over infinity, 1 over big number, of course it's small, 0. And e to the power of 0, it's 1. That means the minimum number, it will be 1. the terms, of course, we will have e to the power of 1/4, 1/5, 1/6, 1/7, 1/10, 1/100. Okay, but never, never, never lower than 1. I can draw it. Oh, I want different color for my, that means it's bounded below 1. We will never touch that value 1. That means what I can do, I can say that all of the terms are bounded between e and 1. Yeah, we like this. We remember from section 11.1. That means that that's the maximum number and that's the minimum. Again, we may manipulate with the inequalities, whichever way we want, depends on the denominator. That means I think I will put 1 and 1 or e. No, if I will put 1, oh, doesn't work, right? You have to help me. I think 10 problems is too much. If I will put 1, all of the, no. Am I crazy? It should be other way. E is the maximum number, right? And then all of the terms this way. All of the terms are lower than e, but greater than 1. Okay, that's what I was. Let me put this. That's the relation. Yeah, you should tell me before. Yeah, e, we can even see e is the maximum. E is the maximum. All of the terms of that sequence is bounded between e and 1. E is maximum. Okay, that means all of the dots are above 1. Because I know you probably know what I wanted. I wanted the inequality this way. Because this is divergent. We know why. Everything what is greater, it's also divergent. Okay? That means that's what I need. My infinite series A sub n diverges by direct comparison test with 1 over n. Okay, important thing. Of course, A sub n, because I'm naming everything A sub n, right? In the previous problems too. Okay? But if I will have possibly n squared in the denominator, I will put e, and I will change the inequality. Convergent, everything what is smaller, convergent. That will make sure that you can like play with these numbers. Of course, always double check, because I put the inequality the other way. Okay, now what I have, exercise 11. And now what we see something similar that we start with. Infinite series from 1 to infinity, 1 over 2 to the n minus 1. That's me now what we have, 2 to the n minus 1. And I know that I have to compare with this one. Okay? But now let's see the inequality. If I'm subtracting something from the denominator, I'm making denominator smaller. If the denominator is smaller, the whole fraction is bigger. Oh, okay. And now, and I think we don't have any other option in this. That means we are not as flexible as in the previous examples. That means this one is definitely geometric one. The geometric series common ratio is 1/2, and it's convergent. Okay, everything what is greater, I don't know. This could be a huge number, could be convergent too. But what is important to say, that direct comparison test doesn't work. It's inconclusive for this example because of that minus. Okay, that means we can't use the direct comparison. Yeah, always check the options, because we will create a question like we will say, oh, you can directly compare. No, you can't. But we can probably think, and the common sense will tell me, what is the difference if I will be like overall looking at the big picture? Subtracting one or adding one, if we're talking about the huge numbers, shouldn't make any difference, right? And we write, this will be still convergent, but I can conclude the convergence at the moment using the direct comparison test. That means what we will be doing, we have another version of the comparison test we will call limit comparison. Okay, limit comparison test. That means I will tell you what it is, but remember, if the direct comparison doesn't work, always try to use limit comparison. If the limit comparison test doesn't work, limit. Of course, we have to look at different tests: integral test, geometric property, telescoping, P-series test, any other test, and we still have few tests for next week. Okay, but at the moment I'm talking about the comparison. That means we have to try the limit, and I can tell you how the limit comparison works, because I don't want you to be confused. Let's see something like that. Let's take a few limits at infinity, because we will compute some type of limit, okay? But I would like you to understand the idea. Limit, let's say e to the n over n squared. Can you tell me what is this limit? This limit is, do you remember the growing rate? Function e to the n works like goes to the infinity much faster. That means if the numerator is winning, it's always infinity. And why? Because this grows faster than the power function. Okay, that means we can see based on the answer, we can kind of get the relation. That means this one is definitely greater than this one in terms of the terms, in terms of the growing to the infinity. Okay, if I will take maybe different function, natural log of n over n. Okay, now we can see that function natural log of n, it's actually slower than n. We remember that, which means denominator is winning. If the denominator is winning, is 0. Right? We have this. But now, what about function like that? Limit as n goes to the infinity, 2n squared plus 1 over 4n squared plus 5. Can you tell me that limit? What is this limit? Oh, we know the limit. 1/2, thank you, because if the degree is the same, we can just take the ratio of the leading coefficients, 1/2. Excellent. That means now we didn't get 0 because denominator is not really leading. We didn't get infinity because numerator is not leading. That means what's happened? Having a finite number, okay, finite number, let's say positive, because we're talking about the positive terms anyway. Having finite positive number, we can conclude that function from the numerator behaves almost the same, exactly the same, like function from the denominator. Like this is kind of like that I'm comparing. I can't say this one is greater or this one is greater. No, both of them behaves the same. We do have some ratio, but doesn't matter. This is quadratic function, this is quadratic function. The slope, I mean the leading coefficients, are not really significant at infinity. That means having a positive finite number, I can conclude, which this is the point, that both of the expressions behaves the same. And now we will talk about the infinite series. That we will have something like that, a sub n and b sub n. And now, whatever I will know, like let's say b sub n, because this will be my b sub n, okay, and this is my a sub n. That's always. That means if b sub n is convergent, and I will create that limit, which I can write it down, I will create a limit of the ratio, A sub n over B sub n. Okay? And I'm expecting a number C, finite number, not zero, not infinity. Okay? That means if I will compute a limit and if I will get like something like that, I can conclude that I can say that if B sub n is convergent, A sub n is also convergent. However, if, let's say, B sub n will be divergent, and I still compute that limit, and I will get a finite number, I can conclude the same. They behave the same. B sub n is divergent, this is also divergent. That means this is the test, limit comparison test, that we can conclude convergence or divergence, just based on this. Because if B sub n is divergent, and we're getting, I'm just repeating, and we're getting a finite number, this means that both of the functions behave the same. This is divergent, this is divergent. If B sub n was convergent, the series B sub n, and we're still getting a finite number, both of them are convergent. Right? That's when we can see that's the limit comparison. We have to take our original series A sub n, divide by B sub n by the new formula, and simplify and compute a limit. Okay, that means let's do it on the other side, but that's the test. And I can show you the test. That's the test. Okay? Suppose that A sub n and B sub n are the series with the positive terms always. And we're creating that limit and computing this limit. And the limit is C, where C is the finite number greater than 0. Then we can conclude either both of them are convergent or both of them are divergent. Divergence, convergence. We know why, right? We know why. Okay, and I can use that space and let me put A sub n over B sub n. And what we had, A sub n is my original one, 1 over 2 to the n minus 1, and B sub n was this one. Let's simplify because it doesn't look good. 1 over 2 to the n minus 1, dividing by 1 over 2 to the n, it's multiplying by 2 to the n over 1. And maybe one more time, 2 to the n, 2 to the n minus 1. Do you know what is this limit? The same function on the top, the same function in the denominator, no leading coefficient, 2 to the n over 2 to the n, it's 1. Right? That means this is my number C greater than 0. I'm satisfying limit comparison, and I can say that since B sub n was convergent, A sub n is also convergent. Let me actually come back to this, and I can say now, because we know that the limit is 1, converges, okay, by limit comparison test. And of course, we're comparing with the nice one, 1 over 2 to the n. But please remember, not direct comparison, limit, because direct didn't work. Okay, that's nice tool. And I have some notes here. Okay, you can pause the video and maybe you can read this carefully. I can also go through, but because this is in your textbook, but I know that some of the professors, some of the instructors, they not really recommend to use the limit comparison test if the limit is 0 or infinity. Okay, we only, because that's actually the comparison, limit comparison. We're really looking for the number greater than 0. However, sometimes you can conclude, but you have to be extremely careful, because having a positive finite number, we can conclude both. We have no problem, convergence or divergence. Having 0, we can only conclude convergence, because what 0 means? 0 means that this is greater. Do you remember? That's what I was writing on the other side. If we're getting 0, we know that denominator is winning in terms of the growing rate. That means if this is, or I can write my other way, the comparison way. That means if B sub n was convergent, then I can conclude convergence, right? But only in this case, 0 and convergence. If I will get infinity, this means that numerator is winning. That means if b sub n is divergent, everything what is greater is also divergent. You may try, as I said, and we will always accept the answer, but however, this is more like generic, general way. Okay? Most of the instructors, they will say, oh, 0, we can't, limit comparison doesn't work. Oh, infinity, limit comparison doesn't work. Of course, it doesn't work if this is divergence or convergence, respectively. But you may also use this. Yeah? Pause the video, think about this, but this is the common way to use it. Okay, and I have 2 or 3 more problems with the limit comparison, and we will be done. Yeah, determine whether this given series converges or diverges. Let's see what we have. First of all, let's look at the sequence 5 to the n, 7 to the n plus 3. That means I will copy this, and of course I will copy this. Plus 3, bigger denominator, everything is smaller, right? If the denominator, oh, this works for the, I want the limit comparison. Let's put minus. My typing is, or maybe I am crazy. If we subtract, okay, now we'll. If we subtracting something from the denominator, we're making denominator smaller, the whole fraction is bigger. Okay, that's what I wanted. Okay? And now, let's see, because we did direct comparison a lot. And what we have? We do have 5/7 to the power of n. Okay, this one is the geometric. Okay, series with the common ratio 5/7, which is less than 1, it's convergent. Okay, something what is greater than my finite number, I don't know. That means direct comparison test is inconclusive. Okay? But we always have the option to compute the limit. If my limit, we know what kind of the limit, this one, a sub n over the new one, b sub n. If this limit at infinity will give me finite number, then I can say that my original series is convergent too. Let's see. 5 to the n over 7 to the n minus 3, and dividing by b sub n means multiplying by the reciprocal. 5 to the n and 7 to the n, I can combine, and we will have 5 to the n times 7 to the n minus 3. But we can see when I distribute, my leading function will be the same, 5 times 7 to the n. Yes, 35. The same function, leading coefficient 1, that means the limit is 1. It's positive, a finite number greater than 0. Then I can conclude convergence. My original series a sub n converges by limit comparison test, and we're comparing with this. Okay, but please remember, comparison works, not direct. I mean the limit comparison, not the direct comparison. Okay, and I have 2 more problems and we will be done. Okay, 4n cubed plus 11n over n to the power of 7 minus 3n to the power of 5 minus 9. That means what I see nice rational expression, n to the 7, 3n to the power of 5 minus 9. And we know that we have to focus on leading terms. Okay? And now let's see if we can get the relation. I'm subtracting something from the numerator on this side. That means I'm making the whole fraction bigger, and I'm even adding on the numerator. That means this is definitely bigger. And if I will simplify my series, I can put 4 in front, and I can cancel out this, simplify n cubed over n to the power of 7. And this is definitely convergent. by p-series test, but everything what is greater doesn't work. Direct comparison test is inconclusive. Okay, we always have a limit. Limit as n goes to the infinity, a sub n over b sub n. Let me create a limit. That means a sub n is 4n cubed plus 11n, n to the power of 7 minus 3n to the power of 5 minus 9. Dividing by b sub n, I will multiply by the reciprocal, and I will put 4. Okay, and we have to, because I will not rewrite, we have to focus on the leading terms. Okay, I will distribute this, and I will distribute just this. I mean everything, but this will give me the leading terms. That means 4n to the power of 3 and to the power of 4 is to the power of 7. And this one is 4n to the power of 7. And I don't really look at the other stuff, just the leading. The same thing, limit is 1. Limit comparison works. Okay, this infinite, I'm just showing you how to use it. My infinite series a sub n converges by limit comparison test, and we comparing with this one. Please include that 4. But even with that 4, we will still get a finite number. That means for the limit comparison, I mean, it's better to keep that 4. But as we can ignore that 4, because we can see if I will ignore that 4, I will have just 1. And the limit will be 4. It's still positive number. It's still fine, but I will keep that 4. Okay? Okay, and the last one, okay, is this one. Actually, let's maybe skip it because it's almost the same like this one. Okay, it's identical. But what I have, I wanted to ask you at the end of the session this question, but you can see the answer. Okay, that means I will finish my session. You can try to get the answer. We have the infinite series, okay, the first one, 5 to the n over 3 plus 7 to the n. We have this one, which we actually did today. We even did this one. And the question is, which of the following statement is true? But we know that both of them converges. Make sure that you know this. Okay, I will finish the session now. Thank you for joining me. Thank you for answering my questions. And please practice. Do not miss any question. It's lots of examples in this session. Okay, thank you.